For steel, we know that the Young's modulus is equal to 2.0 times 10 to the 11 Pascal. And so since both wires are steel in this problem, we're going to be using this. Now the force on the end of the lower wire is the mass hanging at the end of the lower wire, which is 10 kilograms times gravity, which is equal to 98 newtons. This is the force on the lower wire. The force on the upper wire is equal to this mass, 10, plus the additional mass, 5. These masses are at the bottom end of the upper wire, and so we have to add them together, times by g, and this is equal to 147 newtons. And so now we can use the formula for the tensile strain. The tensile strain is equal to delta L over L naught, and this is equal to the perpendicular force over the cross-sectional area times Young's modulus. So we just figured out what the perpendicular forces are for both wires. They're right here. Young's modulus is the same for both wires and is right here. And we're given the cross-sectional areas, but we're given them in centimeters squared. So we have to first convert them into meters squared, and then once we convert them, we can stick everything in this formula to find the tensile strain. I'll go ahead and skip the conversion since it's fairly straightforward. But once you plug in those values here, you get the tensile strain for the upper wire is equal to 1.2 times 10 to the negative 3. And there's no units on that. Since it's a length divided by a length, the units cancel. The tensile strain for the lower wire is equal to 8.2 times 10 to the negative 4. So it makes sense that for the lower wire, the tensile strain is less, since it is carrying less of a load. It's only carrying a 10 kilogram mass. But the upper wire carries both, so we expect a higher tensile strain. For part B, we want to figure out what the change in length is due to the masses. And so the tensile strain is delta L over L naught. So we solve for delta L by multiplying by L naught. So essentially, delta L is L naught times the strain that we just calculated. And so delta L of the lower wire is equal to L naught, which is given in the problem as half a meter, times the strain, which is what we just found, which is 8.2 times 10 to the negative 4. This is equal to 4.1 times 10 to the negative 4 meters. And that's the actual change in length of the wire based on the weight. The change in L of the upper is equal to the same thing, 0.5, the length of the upper wire times the tensile strain of that. When you plug that in, you get 6.0 times 10 to the negative 4 meters. And so it makes sense that the upper wire stretches a little more since it has a much more load carrying it down.